Hi everyone. I would like to, in this talk, present you a small plugin that I wrote, which is r2VMI. And r2VMI aims to transform r2 into Hypervisor Level Debugger, as you can see. So the goal of this project is to overcome the current limitations of our existing tools, and also to build in the future a stealth, cross-platform, and full system analysis debugger based on the flexibility of r2. So kind of a huge ambition, but okay. But first, who am I? I'm a researcher currently at FSecure. I'm working on malware behavioral analysis, and in this context, I've been working on maintaining the Nitro framework. So Nitro is a KVM-based virtual machine introspection framework that will intercept system calls in the VM and trap them. And the framework itself will reconstruct the syscall high-level context by introspecting the guest. And currently at FSecure, we are interested by new ways to do sandboxing, and we are interested into integrating Nitro as a plugin into our sandboxing solutions. So, and this whole work on Nitro led me to create the KVM VMI community organizations on GitHub in order to see what was missing and to help create a defined, an official, let's say, VMI interface on KVM. And the work I've done on this led me to question myself on the debuggers, the state of our debuggers, and can we apply VMI on the debuggers? So the first question is, let's say, is why? Why do you want to create a hypervisor level debugger? We have plenty of tools today to do tracing, let's say, in kernel land or user land. Why do you want to create this new kind of debuggers? First problem you have is that debuggers ads are noisy. A debugger will always modify the execution environment of the debuggee, and you cannot avoid that. It's sort of an observer effect that is unavoidable. So usually, in most cases, it's not a problem until you have to deal with malwares. And the main problem here is that on one side you have malwares that don't want to be analyzed, and on the other side you have the operating system debugging APIs, which are never been designed to be stealth in the first place, and you cannot mix them together. So the more complex the malware, the more anti-debug you will have, of course. So just a quick slide to show you how easy it is to debug a debugger in Windows. You can you can call directly the Windows API. You can scan some memory structures, or you have some syscalls which will have a different behavior whether you are being debugged or not. So detecting a debugger Windows it's trivial. It's really easy. And the consequence of that is that malware analysts will have to spend an extra time to do anti-debug, and this is multiplied by all the diversity of the tools they are using. So in the end, it's kind of a nightmare to maintain. But it's not the only problem. We have another problem, which is that today our debuggers have an incomplete view of the system. The picture you are seeing right now is the new security model of Windows 10. Windows 10 uses virtualization-based security. So it's isolating two different environments and isolating the normal kernel from the secure kernel, which is the virtual secure mode. Now the question is, how do you debug this mysterious secure kernel? The answer is that there is no easy way to do it. And this is just an example. I could also cite PatchGuard, which is protecting the kernel against modifications. And if you try to hook into the kernel, your debugger will be killed and the operating system will crash. So these are just two examples to show that today our operating systems have become so complex that the debuggers are fighting against the security features. And of course, they are losing the fight. So the solution will be to move to the ring below 0, ring -1. So move the whole debugging process to the hypervisor. What we'll gain from that is that we can achieve stealth because we will not use the operating system debug API. Of course, this will bring a lot of challenges. It's very easy to say that, but I will cover that later. And the bonus is that we can use invisible breakpoints using EPT violations. So the second translation layer of the page tables. And the second benefit is that we can have a full system analysis. Since the hypervisor is in control of everything and has the full access to the hardware state, you can see everything and you can also debug the kernel. So you have a kernel debugger on top of that. And bonus, you can debug bootloaders. Of course, your debugger is not available at the early sequence of the boot process. So you can debug bootloaders, basically. But it's not the only benefit. Another benefit is that you can have zero configuration for debugging. I don't want to have any remote debug agent or stub in my VM. I want to be agentless. So I don't want to have to configure and set up my VM, so to set a serial cable or to change the server configuration to install an agent, basically. And also, I want to be able to do on-the-fly debugging, so I don't want to have to reboot my VM to debug it. And just debug it and cancel the debugging on the fly. And finally, latest benefit is that I would like to achieve this cross-platform debugger. So you will be able to use your debugger on top of Linux, Windows, and macOS, and be able to debug the kernel of each one of them. So you have an OS-agnostic debugger. So it's quite an interesting idea, and I would like to build that tool. But now let's review the projects that are already existing. And I've tried to implement this idea of using a hypervisor as a debugger. So I split this into two categories. First, I'll say you have hypervisor-based debugger, while the whole idea is that the debugger is built inside a tiny hypervisor that we're going to virtualize the operating system. So the first example is HyperDBG in 2010. The idea is that you have to compile and install a driver on your operating system, and when you load it, you have a thin layer of virtualization that will virtualize your operating system. And if you press F12, you have access to a text-based interface, which will be your debugger. So it's quite nice. No serial cable involved, and everything happens on the same machine. And then later on, you have PulseDBG, which is more recent, 2017. In this case, the hypervisor is built into an EFI module. So you have to load this EFI bootloader using either a PXE boot or a USB stick. And it's acting as a client-server mode. So you need two physical machines to debug the other one. And it can work in a VM. It can work on a VMware workstation, but it's the only hypervisor that supports PulseDBG because they've done an incredible work to support nested virtualization that PulseDBG works inside of it. The problem I have with these debuggers is that they have been made to debug real hardware and never designed to work with virtual machines. So they don't really fit my use case, unfortunately. They're really interesting, but not for me. Second category, I will say, is VMI-based debugger. So in this case, you are using an existing hypervisor and you try to build VMI APIs into it to introspect the guest. First example I have is Talos Pyrobox tool, released in 2017. So they instrumented the whole QEMU hypervisor, so that they build a dynamic instrumentation engine inside it. So you have plenty of Python callbacks that you can work upon. Like each time a block is being entered or exited, or if a process is being created or removed, you can set a callback on top of that. So it's really, really useful. Problem is like it's emulation based. I would like to have hardware virtualization and run at almost the normal speed. And the second project, interesting, was FireEye RVMI. So they instrumented KVM and added VMI APIs in KVM to be able to do single step and add breakpoints. And also they leverage recall as a debugger and use the interactive Python shell. So it's interesting because you can explore kernel structures in real time and you have an interactive debugger on top of it. The main problem I have with this project is that it's KVM only. And second, the maintainability, because all these modifications that have been done on KVM, I'm not sure that will be going to be merged upstream one day. And second, they are leveraging recall as a debugger. And recall is a memory forensic tool, and I would like to do the contrary, use a debugger instead. So now that we have seen all of these existing projects, what can we do now? What can we do for the design of our debugger? What can we do from here? So for the design, what I would like to have is, I would like to keep the VMI approach, and I would like to improve our VMI actually. This is, well, our VMI. You have recall and a little part which is the debugger, the custom modifications, and they are talking with KVM to instrument it. The approach I would like to reach is doing the opposite. So I would like to take a good debugger or reverse engineering framework and add a small introspection layer on top of it to talk with the hypervisor. And the second modification is that I would like to have an abstraction, the hypervisor VMI abstraction, to talk to the hypervisor so that I can support multiple hypervisor in the future. So for the long term. The question is like how I can have this support for hypervisor agnosticity. Well, you have LibVMI. LibVMI is, think of it as the VMI abstraction layer. It takes care of a lot of low-level details like parsing the page tables, and also offers some basic introspection like translating a symbol to a virtual address by parsing the P export tables. So currently the support is that Xen is fully supported. You can create the registers, the memory, and you have hardware events. And KVM is a bit behind it because there is no hardware event support. But thanks to Bitdefender, they have done amazing patches for this. I think it will come out soon. So the final architecture for my project is that I will use r2 and create two VMI plugins, IO and debug. So the IO plugins will initialize LibVMI, access the memory in the registers, and the debug plugin will deal with the hardware events to attach to a process to single step and set breakpoints. So to use it, you will use r2-d and using a URL with a VMI. Set the VM name and the process name or PID. Now, challenging question, how do you implement such a thing? You have to remember that debugging is a set of API which is also, of course, provided by the operating system. This is an example of Windows, if you want to create a debugger in Windows one day. I don't know. You create a process and you set the debug process flag, and you wait for the kernel to send you some debug events, interesting debug events. The problem is that in our case, the OS, the operating system, will not cooperate with our debugger. We are alone, on our own, and we have to rely on other stuff. So what do we have? Let's do the inventory of what we have. We have the VMI hardware state, we have an introspection layer, and we have our knowledge of operating system internals. What can we build from that? From the hardware state, I can query the registers and the physical memory, and also I can listen to the memory access events, to the interrupts, and also some registers being accessed on special registers, like control registers. From this, I can build breakpoints from the hypervisor. Regarding the introspection layer, I can extract kernel symbols and interesting kernel structures. Also offsets, I want to access some offsets in memory, and I can rebuild my semantic context on top of it. And using the OS internals, I can deduce where the processes are in memory, the process list, the threads, and also what are the kernel APIs involved in the process creation. And I'm going to mix all of that to create my debugger. So how do we implement attaching to an existing process? How do we implement this _attach, r-debug, and a PID? Our first idea is that I will listen to the move to CR3 event. So CR3 is the control register which hold the physical address of a process first page directory. So you can use it as a unique identifier for a process. Each time I have a CR3, I'm comparing it to the process list to see to which process it matches, and then I'm checking for my targeted PID, and if it's the same, I've intercepted my process. And hooray, I have intercepted a process. But it's not done yet, because where am I? I'm somewhere inside the Windows scheduler, because this means the process was being scheduled. So it's a good start, but to continue, we need to build the introspection layer. So how do you build this introspection layer? You have multiple solutions. First, I'm going to use Recall. Recall is very interesting because it's maintained. It fetches automatically the debug symbols from Microsoft, and it has a good API to script on top of it. So the first solution I have is to load a full Python interpreter into my plugin. So call recall functions using Python C API. It's interesting, but you have to write a lot of code, a lot of boilerplate code, just to call it. So I'm not really interested in this solution. Solution 2 would be to run a small RPC endpoint and load recall inside it and communicate with JSON messages with the r2VMI plugin. It might be a good solution for the future, but in the meantime, I was interested by finding, let's say, a middle ground, and I implemented a third solution. So I'm loading the kernel symbols from LibVMI. I created this /symbols command, and this will parse a recall profile predefined that contains all the symbols and offset for the kernel, and load them into Radar 2, into the flag space of Radar 2. And aside of that, I can run an interactive session with Recall using a new address space, which is the VMI address space. And this one is going to work on top of LibVMI to directly work on the physical memory of the guest. So here I'm working on my VM. There's no memory dump. I'm directly working on the physical memory, and I can run PS list in an interactive way. So now that I have some introspection capabilities, I can focus on attaching to a new process, because remember that my main goal is to do malware analysis, right? So I want to intercept a process when it is being created. So how do you implement underscore attach in the case of a new process? You just have to find, let's say, a CR3 that doesn't yet exist in the kernel process list. You check every time, and if it doesn't exist, well, it's a new process being scheduled. So now the question is, how do you access the entry point of this process? That's another problem. But we have Windows internals to help us and our OS internals knowledge. So how does a process is being created on Windows? Let's say it's a two-step process. It's a simplification, but first I'm going to call this API, integrate user process, and this one will be responsible to create the important kernel structures, like the eProcess and the eThread, and then it's going to add them into the kernel process list. And the phase 2 is that this process is one day going to be scheduled, and on this, it will start on this function that's going to continue the initialization of the process address space to load all the DLLs in memory and to switch to ring-free, the user context, and then to finally call the entry point. But now, how do you get to the entry point? What you want to do actually is to read this Win32 start address field. This field is being populated during the call to ntpsp allocate thread, and it contains the entry point of our process in userland. And we know that when we reach k start user thread, we know that this field has been populated and is available. So the solution I had was to let's break on this function. Then you can parse the process, the thread, and read this field. And when it's there, you can break on the entry point, continue, and we will reach the entry point. But it didn't work because this address is not mapped yet. And that's one of the quirks of the problem of, let's say, LibVMI exen. You can only set memory access event only if the page has been mapped in memory. It corresponds to a physical frame. So from that, what can we do? We can try to use the page fault handler and watch multiple times if the page is mapped. You can single step until the ring-free, watch for page table modifications. This is all the things that I've tried, and I'm still trying. It's a bit complicated because the guest sometimes freezes, or crashes. What's the status of my debugger today? What I have is I can intercept a process by name or PID, single step the process execution, set some memory breakpoints if the page is mapped, and load kernel symbols only. And all of that on top of the r2 interface. The issues I have to solve is to, for example, attaching the existing process, I have to find the thread context, I have to debug the VMI state, and other issue in the introspection I have to solve. That's for the future. So now let's switch to the demo. Okay, that's better. Okay, I have r2 VMI here. And this is my VM. So what I'm going to do is to run the plugin on this VM, and I want to intercept explorer.exe. Okay, so I have intercepted multiple processes with logon and finally explorer.exe. So the VM now is paused. You are, of course, inside the Windows scheduler because the rest has to be implemented. But what you can do is to load the symbols like this, and you have access to the whole address space of recall and all the symbols. And what I can do is to add a breakpoint on NT-open file, for example, and let's say continue the execution. So now, already. Okay, so I have intercepted a call to NT-open file. And if you disassemble, you can see that we are here at recall NT-open file, and you can single step the execution. Hop. Okay, so I can single step the execution. That's the state where I am today. And now another short demo that I have, where I will show using r2 pipe on top of the debugger. No, not here. Thank you. Wait, where is it? Okay. Okay, so here I'm running a script which is watching the syscalls and intercepting NT-open files. So first it's running the VMI address space with recall to extract the syscall table dynamically. It's going to find for the NT-open file address, set a breakpoint on top of it, and watch. And each time there is a syscall, it's going to print a parameter associated to the file. So here I'm starting explorer.exe, and you can see that it's intercepting NT-open file and printing the parameter. So why it's slow? It's because I implemented them in the breakpoints in kind of a naive way, where I am setting the breakpoints at the granularity of the memory page. So each time there is a memory access on the memory page, I'm getting an event and going back into the VM. But now, each time there is a syscall, I can print the file associated to it. Thank you. So now to give a conclusion really quick, what is the future for this project? First is to do malware analysis, of course. I would like to mix two interesting stealth sandboxes using VMI and my interactive reverse engineering framework. The sandbox will just be dealing with extracting the classic information while giving to the analyst the possibility to have a fine-grained control over the execution of the malware and inspect everything that's happening in memory, extract the keys, I don't know, all the classical stuff that you have to deal with while being stealth. And of course, it's a multi-purpose, cross-platform, full-system debugger, so have fun, just try it and build your use case on top of it. So thank you to all of these people, Pancake, Maxime Morin, Tamas from LibVMI, Michael Cohen, which helped me integrate the VMI address space into Recall, and Alexei Konovalov from F-Secure Windows kernel team. And I'm available for your questions. Thank you for your attention.
I have a question, Matthew. Here.
Yeah, I can.
Here.
Ah, sorry.
No worries. I'm not.
There's this light, I can see it.
I'm not little. One question. I like it so much, this hypervisor stuff, and I have experience unboxing as well.
Yeah.
And this one, I have one question that is coming to my mind. The problem I saw with hypervisor is the lot of noise that you have to avoid. I mean, you're analyzing one malware, for example, and you have to avoid a lot of Windows events that maybe are not related to the malware execution itself. So what do you think is, as a future line, what do you think is the best approach that we will have to work to avoid this kind of stuff? Because, for example, I thought in create like some whitelisting stuff or stuff like that. What do you think about that?
I didn't explore this topic, but it's an interesting question. I think this is the work of the sandboxes themselves to filter this kind of noise. Here, I think I'm just building the debugger, so to help in an interactive analysis. But yeah, it's more of a question for the sandboxes themselves. I don't have the right answer for you right now. I don't know. Yeah, it's a hard work. You have also worked on this topic, I guess. It could work. Find a solution. I don't know. Yes.
Congratulations for your talk. I like it a lot, and it was quite interesting. And I had two questions. And the first one was in the example, in the demo that you showed, that you were tracing NT open file.
Yes.
You're able to actually trace only one function, or you can trace simultaneously various functions. Is there any limit on that?
No, it's just you set a breakpoint on another function, and you can, of course, trace it. I'm attaching to only one process, but maybe in the future we can attach to all the processes at the same time. We can have this kind of system. But yeah, you can set the breakpoints anywhere in memory, as long as it's mapped, of course.
And another question I had, you were attaching to the process you see in the process name.
Yeah.
What will happen if you're trying to attach without knowing the process ID? You try to attach and there's two explorers. You have to choose them manually.
You can filter by the PID also.
Okay.
But that's the work we can do and improve it, of course.
Okay,
it's just the beginning. Yeah.
Okay, that was it. Thank you.
Okay. Yes.
You said it was possible for the Linux also.
For Linux, yeah, I've only worked for Windows right now.
Yes.
So the question is to test it, but yeah, in the future I would like to have a cross-platform debugger and be able to intercept processes in Linux and macOS, of course.
In your point of view, what will be the challenge that if we implement this for the Linux platform?
It's to build the introspection layer. Here I have a lot of facilities because I'm using Recall, and Recall is fetching the BDBs from the Microsoft servers, and there is only one Microsoft server for all of it. If you think about Linux, the problem here is that it's an open source project, so you never know what kind of kernel you are dealing with. You can never just fetch the symbols right away from one server. It's impossible. So building an introspection layer for Linux is going to be a bit more challenging than Windows. And the funny thing is that introspecting open source system is more difficult than closed source systems.
Okay, thank you very much.
More questions? Thank you very much.
Thank you.